Hello engineers, welcome to the new video of the course, and in this particular video we are going to see that how exactly we are going to design a multiplier with the help of an operational amplifier. Okay, but as far as this particular video is concerned, we are just going to focus upon its block diagram. We are not going to design it and implement it. We are just going to focus upon the block diagram of an multiplier. Okay, so let's proceed further, and I believe that you all guys have a basic idea about a multiplier. So multiplier is a system which actually multiplies the input signal. Okay, so you just come to the input side, and what we can clearly look over here is that we have two input signals, right? We have two input signals, right? And this is a multiplication symbol. I believe that you all guys are quite familiar with it. So what this particular multiplier does, it actually multiplies the two input signals. So that is V1 times of V2, right? So these are the two input signals which are getting multiplied. On the similar note, this is my divider system, so it actually divides these two signals, right? So these are my two input signal, and it actually divides this particular two signals. So V1 divided by V2. Great. Now, as far as this particular video is concerned, we will just focus upon a multiplier only, multiplier block. Okay, so now let me proceed further, and let me just write over here one more time, that is V1 times of V2. V1 times of V2, right? So now how exactly you can move forward to design a multiplier with the help of an operational amplifier. So I request you all guys to pause this particular video over here and try to design it on your own. I mean, try to just design the block diagram of a multiplier with the help of an op-amp by your own. Okay, like till now we had seen lots of circuits like a log amplifier, anti-log amplifier, summing amplifier, subtractor, then inverting, non-inverting amplifier, buffer amplifier, etc. Like we had done lots of things, right? But I request you all guys, that you please pause this particular video over here and try to figure out that how exactly we can get this kind of output or a multiplier output with the help of an operational amplifier. Alright, I believe that you all guys might have tried your best to just design the block diagram of this entire multiplier system. So now it's my turn to show you that how exactly we can proceed further. Okay, so when I say that I want V1 times of V2, so if you could remember, there is one formula in log, right? In logarithm there is one formula. So for time being we'll just take V1 and V2 only. So log of V1 plus of log of V2. So what is this particular formula? I hope that you all guys know the exact answer for this particular formula, right? There is this particular rule in logarithm. If you are adding two log terms, and if the basis of this particular log terms are same, right? As of now we had taken the base as e only. So that means what? That means it can also be written as log to the base of e V1 times of V2, right? We can also write this particular equation in this way, right? Great. Now if you look very clearly, we are able to get this particular multiplication term, right? V1 times of V2, which this is what we wanted, right? V1 times of V2, and we are actually getting it over here. But the thing is that with that we have this particular logarithmic term as well. So we just need to nullify this logarithmic term, and to do so we need to implement one anti-log circuitry as well, or an anti-log amplifier as well. So anti-log of, and I'll just write it in bracket, that is this particular thing, anti-log of log to the base of e V1 times of V2, right? V1 times of V2. And when I say that I'm taking anti-log, that means what? I'm just putting all of these things over e. Okay, so I need to play with the exponential term. Okay, so what I meant to say is this, that is e raised to this entire term, that is log of e V1 times of V2, right? And you see we are easily able to get V1 times of V2 now. V1 times of V2. Okay, I hope you are able to understand this particular concept. Okay, that how exactly we are proceeding further. We just took the help of log, right? I hope that you all guys are quite familiar with this particular rule of log. If you are adding two logarithmic terms and its bases are same, so it can be written as log to the base of e V1 times of V2. So this is basic rule of logarithm. And then we just need to add, or we just need to take one anti-log circuitry as well, or an anti-log amplifier, which will ensure that it nullifies this log effect, and thus we are able to get V1 times of V2. Great. But the point to notice over here is that we had used certain things over here, or certain circuits over here. So very first circuit that we had used is this, that is logarithm, right? So this is the first circuit that I had used. Obviously without that we cannot proceed further. Then the second circuit that I had used is this, that is an adder or a summing amplifier, right? Then the third circuitry which I had used is an Antilog amplifier, So first is what? First is logarithmic amplifier, second is adder or a summing amplifier, which you can say, and third is an Antilog amplifier. So I'm just writing it in short form, Antilog amplifier. So these are the three major important blocks if you want to design or if you want to implement a multiplier with the help of an operational amplifier. So let's proceed further and let's see how exactly we can do so. So yeah, you see over here we have this particular input, that is V1, right? It is fed to the logarithmic block. Similarly V2 is fed to the logarithmic block. Now let's try to figure out what will be its output. Okay, what will be its output? Let's try to figure it out. I'll just take this particular block into account. So let me just paste it over here. Let me just move this entire thing over here. Okay, great. So now let's assume that the output that we may get from this particular block, it is X, and the output that we may get from this particular block is Y. So we'll solve for X. X is nothing but log to the base of E times of V1, right? And Y is nothing but log to the base of E times of V2, right? Great. But this is not the case. Why? Because if you could remember, we are trying to design logarithmic amplifier with the help of what? With the help of negative feedback, right? We are actually using a negative feedback, right? Negative feedback. And also if you could remember, the output for the logarithmic amplifier, it was minus log of V in, right? Minus log of V in. So if you could remember, V out was nothing but it was minus of Vt times of log, right? And over here we had certain terms, right? I think V in divided by Is times of R in, right? If you could remember. So this was the formula for logarithm. But if you could remember, see, we are getting one negative sign over here. Why? Because we were trying to design the logarithmic amplifier with the help of negative feedback, and same thing we are doing it over here. So instead of getting a positive symbol over here, we will get a negative symbol. And as of now I'm just neglecting all of these terms, that is Vt and Is and Rin. We are just focusing upon log and V in. Okay, we are not at all focusing upon these terms. See, we are not focusing upon Vt and Is times of Rin. We are just focusing upon the block diagram, right? So don't get panic that why exactly I'm not writing these particular terms. Okay, so now let me erase all of the thing. Let me erase this as well. Okay, now let me just add the negative sign over here. So let me move it somewhere over here. Let me move this as well somewhere over here. Now let me just add one negative sign. So this will be X is equal to minus of log to the base of E times of V1, and my log to the base of E, this is V2, right? Great. Now you see it is getting or it is being supplied to the adder, right? It is being supplied to the adder. So now let me take this particular block into account. Let me take this particular block into account. Control C. Now let me proceed further. Control V. Yeah. Let me just show this particular line over here. Yeah, great. So let me move it somewhere over here, and this is X, right? This is my X, this is my Y, right? This is my X and this is my Y, and let's assume the output that we are getting, it is Z, right? So we need to find out what this Z may be. And as you can clearly look over here, this is my adder, right? This is my adder. But if you could remember again, when we design a summing amplifier with the help of op-amp, so our output was V out is equal to minus of V1 plus of V2, right? Minus of V1 plus of V2, right? If you could remember this particular term, obviously there were certain gains as well, RF by R1 or 1 plus RF by R1, right? So as of now, I'm neglecting that, but we were getting certain negative sign. So it indicates that we had negative feedback, right? We had negative feedback or basically we had given op-amp, or basically we are operating op-amp into the negative feedback. Just remember this, okay? So now what will be z? Z will be equivalent to minus of x plus of y, right? This will be my z. What is my x? You see, x is minus of log to the base of e v1. So let me just write over here. So this will be minus of, what is my x? So let me just write it in this particular bracket, log to the base e v1 plus just a second, yeah, it was minus, sorry, my bad. So let me just move it somewhere over here, just a second. Yeah, so this is minus, right? This is minus log of v1 to the base of e, and again we have minus log of v2 to the base of e, right? Getting my point? And then we are closing the bracket. So this entire term is my x and this entire term is my y. So this entire term, see, this entire term is my x and this entire term is my y, right? So it is nothing but x plus y only. Okay, getting my point? Okay, so what I can do, I can actually take this minus sign common, or you can actually multiply this minus sign over here, right? So let's do that. So this will be minus of minus will be plus, so log to the base of e v1, and this was minus, so minus of minus, that will be plus once again, so plus of log to the base of e times of v2. Getting my point? So what is my z? Z is nothing but log to the base of e v1 plus log to the base of e v2, right? So I can also write this particular equation as, let me move this little below. Yeah, so I can also write this particular equation in this way, that is, let me change the color. Yeah, so I can also write this particular equation as log, see over here we had already solved it, log of v1 plus of log of v2. It can also be written as log of v1 times of v2, right? So this can also be written as log of v1 times of v2, right? Log of v1 times of v2, obviously to the base of e, right? Getting my point? So you see, we are able to get the multiplication of the two input signal, but we have this log term, involved over here. So what we need to do, sorry, let me add one more slide. So we just need to take one antilog amplifier. So let me just take this antilog amplifier. Just a second. Let me just take this particular block over here, Control C, and let me paste it over here. Yeah, Control V. So we have Z over here. We have Z. Sorry. Yeah, we have Z over here, and let's assume the output that we are getting is maybe A. Okay, A. So let's see what exactly this A can be. So what is my Z? Z is nothing but log to the base of e v1 times of v2, right? Okay, so what will be my A? Since it is an antilog amplifier, so A will be equivalent to e times e raised to z. What is my Z? Z is nothing but, let me write it little down, let me take it little below. Yeah, A is nothing but log to the base of e v1 times of v2, right? Okay, so now what you will do is that you will directly write it as v1 times of v2, and you will say that, yeah, we had actually finished the block diagram, we had actually understood it, but this is not the case. Again, there is one point which we generally neglect, and that is this. Okay, so sorry, that is this. See, since this is an antilog amplifier, and again we are designing antilog amplifier using op-amp with the help of negative feedback. So this particular point is missed by lots of instructors out there, and generally most of the books, they just fail to mention this particular point. So over here we have one negative sign, right? Over here we will have one negative sign, and that's why the output will be, instead of v1 plus of instead of v1 times of v2, we will have output as minus of v1 times of v2. So this will be the output. So if you want, you can keep this particular output, because our main intention was to get the multiplication of the two input signal. Or else what you can do is that you can actually apply a buffer amplifier or the inverting amplifier with the gain of 1, right? So the signal generator, what it does is that, see over here, I had mentioned, right, where it is, yeah, over here I had mentioned that this is my signal generator. So if over here you are getting minus of, let's suppose minus of A, right, this is my output. So signal generator will just change the sign and you will get plus of A. So over here you were getting V1 minus of V1 times of V2. So over here you will get plus of V1 times of V2. So that's the only thing what signal generator does. Okay, so you see we are getting output as V1 times of V2, and this is what we wanted. Okay, and now I believe that you understood this particular concept, that how exactly we are designing, or how exactly we can proceed further to design a multiplier with the help of an op-amp, right? So you just have a look over here. This is the entire circuitry which I just taken from the Google. This is one circuit. So yeah, you see over here, this is my log amplifier, right? Just see this particular part, this entire block from here to here, right? And again from here to here. Let me just increase its size. Yeah, so you see this is my V2, this is my V1, right? So this is the log amplifier. Let me just write over here, this is my log of V1, okay, obviously minus of log V2, right? This is my log amplifier. And then we have the summing or the adder, right? Summing amplifier or an adder. So this is my summing amplifier or an adder, right? So this is my adder or an summing amplifier, and what we will get is this, that is this particular term minus of C, minus of X plus Y, or rather yeah, Z, log of V1 times of V2, right? So this is the output that we may get over here, right? Over here we are getting output as log of V1 times of V2, right? So let me just write over here, we will get output as log of V1 times of V2 base of E, right? And this is my Antilog amplifier, this entire block from here to here, this is my Antilog amplifier. This is my Antilog amplifier, right? This is my Antilog amplifier, and over here we will get minus of E raised to log of V1 times of V2, right? V1 times of V2. So in short, we will get minus of V1 times of V2. Okay, over here in this particular circuitry they had not shown the signal changer circuit, right? That means you can actually connect one buffer amplifier over here, which will just instead of minus V1 V2, you will get plus of V1 V2, right? So they had not shown over here, but that is also fine. Okay, because our main intention was to get the multiplication of the two input signal, and this is what we can get over here. Okay, great. So I believe that you understood that how exactly we can proceed further with this particular logic of log and anti-log amplifier, and how exactly we can design a multiplier with this particular logic, right? We had done nothing special, or no, it's not like a rocket science. It's just the basic mathematical rule which was present. We just tried to apply that. And yeah, we got the desired result as we wanted. Okay, great. So I really hope that you understood the concept of multiplier, that how exactly we proceed further, and what all things like in what all things we face challenge, and how exactly we overcome that particular issue, right? Great. So I believe that you understood each and everything that we had discussed till now in case of multiplier. So what I'll do, I'll just end this particular session over here, and in the next session we will focus upon the divider circuit. Okay, but it's my request to you, the divider circuit is almost 90% same as the multiplier, but we just need to change one circuit over here. Okay, so it's my request to you all guys that you please make you please try to design the divider block or the divider system using op-amp by your own. Okay, at least the block diagram. I'm just focusing upon the block diagram. So it's my request to you all guys that you please try to design the block diagram of a divider circuitry on your own. Okay, and in the next video I will show you that how exactly we can design a divider block diagram with the help of an op-amp circuitry. Okay, so I really hope that you understood the concept that we had discussed in this particular session. But still, if you have any doubt, if you are facing any difficulties anywhere, it's my request to you all guys that you please ask those particular doubts in the communication section. I will be happy to help you out there. Okay, so thank you for listening patiently. I'm ending this video over here. Thank you.